For several hundred years, astronomers have kept track of the number of solar flares or sunspots that occur on the surface of the sun. These are ejections of massive amounts of energy that flare out and disrupt our electromagnetic field here on the Earth. The number of sunspots in a given year varies sinusoidally from a minimum of about 10 per year to a maximum of about 110 per year. Between 1750 and 1948, there were exactly 16 complete cycles of these solar flares. So let me just show you an article, fairly recent article from the Star that I saw in 2010. That might not seem recent to you, but it wasn't that long ago. And there's a graph of the occurrence. So the height of the graph represents how many solar flares occurred during that year, and you can see that, or during that time period, and you can see that there is this sinusoidal pattern. Now, why is that of any concern? Well, it turns out that since these cause a major disruption in magnetic activity, then we have the potential of knocking out our power grids, our satellites, our GPS systems, cell phones, computers, internet, all that could be disrupted by these solar flares. There was a major occurrence in 1859, and just a description of that. On that morning, Richard Carrington was capturing the likeness of an enormous group of sunspots. Suddenly, before his eyes, two brilliant beads of blinding white light appeared over the sunspots, intensifying rapidly, and became kidney-shaped. Realizing that he was witnessing something unprecedented, and being somewhat flurried by the surprise, I hastily ran to call someone to witness the exhibition with me. On returning within 60 seconds, I was mortified to find that already much had changed and enfeebled. He and his witness watched the white spots contract to mere points and disappear. Only 5 minutes had passed. Just before dawn the next day, skies all over planet Earth erupted in red, green, and purple auroras so brilliant that newspapers could be read as easily as in daylight. Indeed, stunning auroras pulsated even at near tropical latitudes over Cuba, the Bahamas, Jamaica, El Salvador, and Hawaii. These are called northern lights. You normally don't see them except very far north countries. Even more disconcerting, telegraph systems worldwide went haywire. Spark discharges shocked telegraph operators and set telegraph paper on fire. Even when telegraphers disconnected the batteries powering the lines, aurora-induced electric currents in the wires still allowed messages to be translated. What Carrington saw was a white light solar flare, a magnetic explosion on the sun. Okay, so now, and here's a picture of one, a more recent one. So what's the issue now? If we had one of that magnitude, a solar flare of that magnitude these days, it could knock all of the satellites on Earth out. We've had some incidents, a more recent scientist who said, more than 35 years ago, I began drawing the attention of the space physics community to the 1859 flare and its impact on telecommunications, says Louis Lazzarotti from Bell Laboratories. In 1972, a huge solar flare knocked out long-distance telephone communication across Illinois. That event, in fact, caused AT&T to redesign its power system for transatlantic cables. A similar flare in 1989 provoked geomagnetic storms that disrupted electric power transmissions in Quebec, blacking out most of the province and plunging 6 million people into darkness for 9 hours. In December 2005, X-rays from another solar storm disrupted satellite-to-ground communications and global positioning systems for about 10 minutes. That might not sound much, but as Lazzarotti noticed, I would not want it to have been on a commercial airplane being guided in for a landing by GPS or a ship being docked by GPS during those 10 minutes. So this is an issue that scientists are having to deal with. How do you prepare for solar flares? How do you track solar flares? So this is actually a really important application of a sinusoidal function. So let's go back to our problem here. Here's the information we're given. We have a high and a low value of how many solar flares per year, and we see that between 1750 and 1948 there were 18 complete cycles. So we can figure out the period of a sunspot cycle by doing 1948 minus 1750 and dividing it by 18. And when you do that, you find out there were, the cycles are 11 years. So assuming that the number of sunspots per year is a sinusoidal function of time, and we can see from data collected that it appears to be, and that a maximum occurred in 1948, find a particular equation for the number of sunspots per year as a function of the year. Okay? Now, when you're dealing with time, putting in 1948 and 1750 and 2001 as your x values are very large numbers. It actually makes sense to just start counting from a certain date. So let's just say that t equals 0 in 1948. So that will make that time 0, 1948. So we're going to represent, and we have a high point there. The high point is 110. The low point, I scroll back up here, the low point is 10. We know the period is 11. So we always want to do our application problems in radians. So we know then that 2 pi divided by b gives us the period. So b equals 2 pi over 11, or pi over 5.5. Now the reason you might think, well, why do I want to have a decimal in the denominator? Why don't I just leave it as 2 pi over 11? It really, I guess it doesn't matter either way in this case. However, sometimes when you're solving equations and you end up having to solve by multiplying by 11 over 2 pi, students don't put the 2 pi in parentheses and got mixed up, so I tend to prefer this with just the pi over 5.5. We're not getting to solving equations yet, but that will come later. So let's say that f of t, so our time, is, we need our sinusoidal axis. Halfway beat, this is a distance of 100 altogether. So if I were to draw the high and the low, so let's just actually make a sketch of the graph here. So my low is 10, high is 110. There's a difference of 100 here. So the amplitude is going to be 50, and this would be 60. Okay, so sinusoidal axis would be 60. We're going to start at a high point at year 0, which is 1948. We have an 11-year cycle, so at time 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which would be the year 1959 in time, when t is equal to 11. That would be the next high point. We'd have a low point halfway in between. So at 5.5 years, 1, 2, 3, 4, 5. So about here, 5.5 years, we'd have a low point. So there would be our sinusoidal function. We could write this as f of t equals 60 plus 50 cosine of pi over 5.5x. Since my phase displacement, I called 1948 times 0, then I could figure out then I don't need to have a phase displacement. So how many sunspots are there expected to be this year based on my sinusoidal model? Okay, so I need to figure out what 2020 is. So 2016 minus 1948, and then that's going to be my t value. That will be how many years since the solar spot, the last high point. I mean, that's how many years since we started counting from that high point. So this is 68 times 68. So I'm just going to put 68 into my function. And there's a really easy way to do this on the calculator, and we're going to look at graphs, and we're going to look at also on the calculator using a function on the calculator. So let's do that right now. Go to the graph, go to a graphing page on the calculator, and we're going to type in our function. I'm going to pause while I do it. Well, if you're like me, you got this really messy looking graph. Obviously we need to change some window settings. A quick way to change your window settings is to just right click on, or I'm sorry, not right click, just double click on the actual grid value at the top, or the axes endpoints, and then you can just change those. So I know it goes up to 110, so let's make that 120. Okay, I'm going to be wanting to go to maybe over 100 years from 1948, because that would get me to 2048. So let's make this 100. And then you just tab around to the other numbers, and I think somehow I missed that other number. So if we... Nope, I'm going to just go to my Windows settings because it's getting a little messy now. So go to my Windows settings. I want my X scale, my Y scale doesn't, it'll just do automatic is fine. My Y min, negative, it goes to 10. Let's just make that, I'll just like it negative 10. That's fine. That's good enough. And Y max, that looks good. Okay, so here's my graph. Now I want to know 1948, which was 68 years. I'm sorry, not 1948. 2016, which was 68 years after 1948. So I can trace the graph and do this, just trace, graph trace, and I can just type in 68. When I type in 68, it tells me the amount of sunspots that year. Notice if I typed in 0, I would get the 110, the high point. If I wanted to know 2020, I would type in 72 because that's 72 years after 1948, and that would give me a negative value. That's odd. Oh, because I did my equation wrong. Okay. Some of you are probably yelling half point, have been yelling half point for a long time. This is supposed to be 60 plus 50. There we go. That makes a whole lot more sense because there aren't negative numbers of sun flares. And so let me just kind of drag this down. There we go. So my value obviously was wrong there. Menu, trace, graph trace, and so 72 would be 12. It'd be actually at a minimum in 2020. And if I typed in the 68 for this year, we're just coming down from a maximum. So when would the next maximum be? Well, if I just kind of scroll along here, I can get up to, looks like about 77 years after 1948 would be our next maximum value. If I put in 77, it looks like that would be it. Yep, so 1948 plus 77. So in 2025, we'd be a little concerned about our sunspots here. So let's go back, and obviously I need to change my equation here. I did this, I typed it in, I wrote it right, but I typed it in wrong. Okay. So in the year, I've got those down. Hopefully you guys got those down. I'll come back and write those on the paper. So let me pause a second and get those. It looks like we've actually answered 3 of the questions for this year, for the 2020, and when's the next year with a predicted maximum was 2025. What is the next year in which there's predicted to be about 35 sunspots? So once again, going to the graph here, starting with this year, which was year 68, and then kind of going down here, it looks like maybe year 69 or 70. So if I put in 70 or 69, one of those 2 years would have done it. So going back to my wrong spot here. So maybe about 2017 or 2018. So year 69 or 70. So using the graph. Okay. To the right is a graph of recent sunspot activity. Do we match? Do we see a high in... Actually, this is not that recent, so I'm not really sure why I asked that question. So I think we'll just stop right here.